Oops. All right, so we are starting chapter 19. We finished chapter 18, where we saw how aromatic compounds have a special stability associated with the resonance and the molecular orbitals, where their pi electrons exist. And this slide here is a reminder of some of that conceptual stuff we talked about. We said that a typical pi bond holds the electrons farther away from the nucleus. It doesn't stabilize them very well, so it starts relatively high in energy, and it doesn't take a strong energy collision to add the bromine across the pi bond, right? So this is an addition reaction we saw last semester. And then we said when you have an aromatic ring, you don't really see the same reaction because the electrons are much more stable and in those molecular orbitals created by the p orbital overlap. There are some reactions that this aromatic ring will undergo, though, and that's what we're going to talk about in this chapter. So while an addition reaction is not common because the addition reaction produces a product that's no longer aromatic, it's no longer fully conjugated all the way around the ring, thermodynamically, that would just favor the reactant side, and it wouldn't get much of that product produced. However, here we have a substitution reaction because we're removing a hydrogen and replacing it with the bromine. So we're using the same reagent. This iron atom is going to act as a catalyst. And the key here, though, is that the aromaticity is maintained. So it is lost during the reaction, which we're going to see here in a little while, but then it reforms. So the product can be favored, or at least not disfavored. And since bromine is relatively unstable compared to a lot of other sigma bonds, the carbon-bromine bond is more stable. That's what allows us to be a product-favored process. So we're going to look at these reactions where we end up substituting a hydrogen on an aromatic ring for some other atom or grouping of atoms. And there's a variety of reaction conditions that will allow that to occur, and it will give us more options when we're setting up syntheses, and that's also what Lab 4 is about. So here's a brief view of some of the functional groups that can be installed on a ring in a substitution reaction where you remove a hydrogen there and replace it with some other group. And these are called electrophilic aromatic substitution reactions. So we covered the substitution part, right? We're substituting some other group for that hydrogen. It's obviously aromatic because it's occurring on an aromatic ring, and we wouldn't see these reactions on other types of compounds that don't have aromatic rings. And it's electrophilic specifically because in order for the hydrogen to be replaced, it has to react with an electrophile. So it's not that the ring is electrophilic, it's that we're adding an electrophile. In each one of these cases, it would be a different electrophile, but the main pattern or theme here is, depending on the electrophile and how much quantity of positive charge it has, because this ring is electron rich, even though there's resonance, stabilization, and molecular orbitals that stabilize those pi electrons pretty well, the HOMO pair of electrons, the highest energy ones, are still bonding molecular orbital electrons, but they're not the most stable ones. So one of those pairs of electrons can start making a new sigma bond with an electrophile, and then we'll see how the mechanism goes from there. So the main thing here is that the electrophile is something that the ring is reacting with. All right, so let's take a look at the electronics of these types of reactions. So we're looking at an aromatic ring. is it more likely to be a nucleophile or an electrophile? And the answer is it's much more likely to be a nucleophile. So there's no real areas of partial positive here. If I did have a nucleophile, it was ready to share electrons, what could it do? Well, at best, it could come in here, bond to a carbon, but that would push one of these pi electron pairs onto the neighboring carbon. So that would create a negative charge on a carbon, which is pretty unstable. So if there's, even though it's stabilized by resonance, it's still only going to be spread out over 3 different carbons. So we know from the discussion we had on how to stabilize a negative charge that carbon is not an atom that's very good at stabilizing a negative. So if we had some way of shifting that negative onto an oxygen or an even larger atom like a sulfur or something, that would be much more stable for the negative charge. So this is not something we expect to occur. So I just want to point that out. There's a reason why the aromatic ring is not a good electrophile. It doesn't have a positive to attract in the negative of a nucleophile. And if a nucleophile does attack, it creates a pretty unstable carbanion intermediate. So the aromatic ring is much more likely to act as a nucleophile. If I have some electrophile, the ring could attack it, and that would produce a different intermediate where the electrons would now be shared with the electrophile. So if this electrophile were unstable enough, it could really attract those electrons out, and when it does, they'd be pulled away from this carbon, which would only have 1 hydrogen attached to it. And so that would create a carbocation. The carbocation would be kind of unstable, but we would really have to compare it to the stability of the initial electrophile. As long as the initial electrophile were similar or more unstable than this carbocation, it could attract those electrons and form this carbocation, which is resonance stabilized. It breaks up the aromaticity of the ring, so that's relatively unstable, but as long as we can reestablish the aromaticity of that ring, it should not be a prohibitively unstable intermediate for the structure to go through. So we think of the ring itself as a nucleophile in these reactions. And so we're talking about reacting with bromine. Let's take a look at bromine. Is bromine a good electrophile or a good nucleophile? Well, really, it's not really great at either of those things. It doesn't have a large negative. It does have a lone pair, so we could imagine that lone pair attacking an electrophile and sharing electrons with it. But that would put a positive on the bromine. That's not especially stable. So it'd probably be likely to pull those electrons back. Can a bromine accept electrons? Can it act as an electrophile rather than attacking an electrophile and acting as a nucleophile? And the answer there is yes, because if you've got 2 bromines sharing electrons, one of those makes a great leaving group. It can leave with the electrons and create a Br-, which we know is quite stable since it's so large, has a complete noble gas configuration, and is a relatively electronegative atom. So if a nucleophile is present, like an aromatic ring, it can attack one bromine and push the shared electrons here onto the other bromine. So we think of Br2 as more likely to be an electrophile, and the aromatic ring is more likely to be a nucleophile. And when we bring a nucleophile and electrophile together, that's when we see a reaction. In this particular case, we did say that we need iron as a catalyst. And what happens with the iron here is at first a reaction with bromine to produce iron bromide. Right? So the iron has these valence electrons in its outer energy level. It has 2 in the 4th energy level, 2 electrons in the 4s, and it has 1 electron in the 3d that it doesn't need, because if it loses it, it'll have a half-full subshell, which is relatively stable. So a lot of times we see iron losing a total of 3 electrons to make a 3+ charge. That means its remaining electrons are all in the 3rd energy level, and they're all making the subshells there full or half full, which is relatively stable. So if the iron gives electrons to the bromine, a bromine can pick up those electrons one at a time and become a Br minus. So that reaction occurs pretty readily. You have iron, which is pretty easily oxidized, and bromine, which is a pretty good oxidizing agent because it's good at picking up electrons and oxidizing the iron to form iron bromide. And the iron bromide we could think of being as partly ionic and partly covalent. If we think of it as being ionic, we would think of the iron having a 3+, and there'd be 3 Br minuses around it, and that would allow for a charge balance in the repeating chemical unit there. But since the iron's positive charge is a large quantity of charge, and it does have space in the 3rd energy level to accept more electrons, there will also be some degree of sharing, or to some extent there will be a molecular orbital in which those electrons surround both atoms. So we can also represent those as covalent bonds that would be highly polar, creating almost full charges on the bromines and a very large quantity of positive on the iron, close to a 3+, somewhere between probably 2+ and 3+. So there's a lot of charge on that iron as the electrons get pulled away from it, and it almost exists as a full 3+ ion. And all of that positive charge can attract electrons in from the bromine. So this reaction probably favors the reactant side, because forming a negative on it, a metal usually is not very stable. Putting too many electrons around there, the bromine would probably start grabbing those electrons back and leaving. So a lot of the molecules will be in the form of Br2, but some small quantity of the Br would end up connecting to the iron. And that creates a positive on the bromine. So we were talking over here about how bromine's a pretty good electrophile. Mainly we said that because there's a good leaving group. If a nucleophile attacks it, the other Br can leave and be quite stable. But it's not a great electrophile because the Br2 doesn't really have a large quantity of positive, right? When we think about Br2, or really any neutral halogen molecule, it's not polar. It doesn't have a dipole. There's no opposite charges on opposite ends. So there's no area of strong positive charge to attract a negatively charged nucleophile in. The cloud of electrons can shift randomly, so there can be a temporary dipole. If the shared electrons shift one way, that can create a temporary partial charge, but it's not much of a charge to attract the nucleophile in. So the role of the iron here is to create a more of a positive charge on this bromine atom. And you could imagine this bond breaking and the electrons swinging out here to balance that charge, which would give you this, but this would be really unstable. So this may form in a very small amount, but it makes the bromine an extremely good electrophile. So that would be very reactive because the bromine doesn't have a noble gas configuration any longer. It would attract electrons out here. Most of the molecules, though, would not really exist in this form. Most would exist in this form or in this form. And this is still very electrophilic, though. So what will happen with this structure here, which is this structure right here, is that the positive charge on this bromine will attract the shared electrons so strongly that it will create a very large partial positive here. And that will attract the negatively charged electrons from the pi system of the ring into that bromine to attack. So this is where the nucleophile and the electrophile collide to create the new sigma bond. And that makes this Br an even better leaving group, because now when it leaves, it doesn't take on a negative charge. It just becomes neutral. So in this process, the FeBr3 is acting as a Lewis acid. What does that mean? A Lewis acid is a molecule that can attract in more electrons, right? So when we were talking about its structure over here, we said because these bonds have some ionic character and because they're so polar, the iron has a large quantity of positive charge. And since it can still accept more electrons into its valence energy level, it makes it a Lewis acid. A Lewis acid is nothing more than an electrophile. This bromine's acting as a nucleophile, the iron's acting as an electrophile, and what makes it electrophilic or a Lewis acid is the large quantity of positive charge that it has to attract in new electrons. Sometimes aluminum bromide is used, and that's for the same reason. The aluminum bromine bonds are also extremely polar, and that means that there's a large quantity, almost a full 3+ on that aluminum as the electrons shift almost completely away from it. And so that also can attract in a pair of electrons in the same way that the iron does here. So those are Lewis acids. They're also electrophiles. In this case, they're going to temporarily bring that bromine in, as we're going to see. So then what happens here is a resonance stabilized carbocation form. As we said, the pi electrons would be attracted to this bromine so that these electrons could move out and stabilize that charge. And so, that's going to form FeBr4 that will have an overall negative. And it will also make a new bond to the bromine between one of these two carbons and the bromine. It doesn't really matter which. So if this carbon is the one that attacks the bromine using this pi electrons, the pi electrons are pulled away from this carbon. And that's why this carbon now ends up with a positive charge, right? There's only 3 pairs of electrons around it. It's not a complete noble gas configuration. It doesn't have a balanced charge. It's a carbocation. But it's resonance stabilized because this pair of electrons can shift up there. And as that occurs, it'll shift the positive here. Then this pair of electrons can shift there, and as that occurs, it'll shift the positive there. So we'll end up with a resonance hybrid that would look like this. So we would show all of the positions where the electrons are spread out over with a dotted line. That does not extend all the way around the ring because here I've got an sp3 hybridized carbon. So there wouldn't be a p orbital there to overlap to extend the resonance, only on these other 5 carbons of the ring. And since the positive charge is on carbon 2, 4, and 6, those would be the carbons that would share that partial positive. So this would be the hybrid. It doesn't look bad. It lost the aromaticity of the ring because the ring is no longer fully conjugated all the way around. So it's pretty unstable compared to what it was initially when it was aromatic. But it's not nearly as unstable as a lot of carbocations because at least the carbocation is stabilized over 3 carbons through resonance. So that can form, that's called an uranium ion, or a sigma complex. So the textbook uses both of those terms. So you want to be familiar enough with those terms, or if I ask you to draw that resonance hybrid for the uranium ion or sigma complex, or the contributors for the sigma complex, that you know what I'm talking about. So then what would happen next would be to re-aromatize the ring. And so this is where the catalyst is regenerated. Right? We started with FeBr3. If it's a catalyst, it has to be regenerated in the end. So what we were saying before was when the iron from the FeBr3 picks up another bromine, and that bromine takes those electrons to become a Br, the 4th bromine connected to that iron, that creates a negative charge. And so that's not the most stable structure. And if bromine pulls electrons away from that, it'll balance out the charge again, which is better for it. So that electron pair can pick off a proton and swing electrons back in to re-aromatize the ring. And that is the step where this proton is removed, fully completing the substitution of the bromine for that proton once it's gone. The downside here is you form HBr, which is a strong acid, and so that's pretty unstable. But re-aromatizing the ring makes the product pretty favored. And if we look at the overall reaction, where we have Br2 and the aromatic ring and the FeBr3 catalyst, starting with the catalyst, ending with the same catalyst, well, that's not going to change which side of the equation is favored thermodynamically. Both rings are aromatic, they look pretty stable. So really, ultimately, what this comes down to from a thermodynamic perspective, if we're just comparing the reactants versus the products, is the sigma bond in Br2 more stable, or is the sigma bond in HBr more stable? And it turns out that the HBr, even though it's a strong acid, is a little bit more stable than the Br2, and so that's why that process is product favored when it reaches equilibrium. And since none of the intermediates are especially unstable, because they're either stabilized by resonance or the FeBr4 is relatively stable, there's no reason why it shouldn't work kinetically as well. So we have a thermodynamically favored process that doesn't go through especially high transition states, so it's kinetically feasible, and that yields a nice product. And so we can control, to a fair extent, what groups now we put onto an aromatic ring. We can start to build up structures. Just to point out the substitution product versus the elimination, right? So we're saying the difference between the reactants is the Br2 is a little bit less stable than the HBr that's formed, right? So that's the main reason why this reaction is product favored or exergonic. But we also said we could at least envision the addition across a pi bond of a Br2. That would be an anti-addition because of the mechanism. And so that would produce this product. But since that product is not aromatic, it doesn't have the special stability of the aromatic ring. So re-aromatizing the ring in the last step of that mechanism makes all the difference. If we weren't able to re-aromatize the ring, or if we ended up with a product that's not fully aromatic, it would be significantly less stable, and that would be a situation where the delta G for that reaction would be endergonic, creating a reactant favored situation. So that's the reason why thermodynamically these reactions go toward substitution products rather than addition products. We can also do the same with chlorine. Typically with chlorine, you see the aluminum chloride catalyst in textbooks. Basically, it's doing the same thing. So we want to draw the mechanism there. So what happens first is the aluminum chloride. We can represent those bonds as ionic or covalent. Either way, there's a huge amount of positive on that aluminum, so it's able to attract in a lone pair to form a very similar structure to what we just saw with the bromine and the iron. That creates a formal positive there and a negative here. Although really, the electronegativity differences here are pulling so many electrons away from that aluminum, it ends up with a net actual positive quantity, but it would have a formal negative if we imagined it sharing 4 pairs of electrons. And so that sets this chlorine up as the electrophilic site, because now the ring can attack here and release this chlorine and alleviate its formal charge. So that would give me the ring now bonded to a chlorine, creating a carbocation. They'll be stabilized through resonance, and the aluminum would then have 4 chlorines attached. So that's not that stable, and one of these chlorines would fall off of there. It would be electronegative enough to pull electrons away, and it could use those electrons to then rearomatize the ring. So the rearmatization step, students often write incorrectly, so I want to point that out. And it's easy to make this mistake because the hydrogens are usually not shown. So it's another example where it's super critical to draw in the hydrogen in the area where there's a change occurring. Right? In the benzene ring, to start off with, there's a hydrogen on every one of these carbons. There's only one hydrogen. So to stabilize this carbocation, it needs more electrons. It has 2, 4, 6 electrons. It needs 8 to make a noble gas configuration. So one thing you should not be doing is to try to fix that carbocation by taking off the proton on the same carbon as the carbocation. That's not going to fix it. And so what I know I'll end up seeing some people do is something like this. This is not correct. You can't have the chlorine pull off this proton and re-aromatize. It looks okay, but it's not, because there's a hydrogen here. If you push electrons in here and make a new bond, it's going to be a 5-bonded carbon. So do not do that. You've got to have the chlorine pull off the proton from the same carbon that's undergoing substitution. We're substituting this new group for the proton. And so it has to be that side that rearomatizes, right? Because we have to push electrons in toward the carbon that needs them, not push electrons in toward a carbon that already has 4 bonds. So make sure you do that when you're working through the mechanism. And so that would be product favored for the same reasons we saw for the bromination. The HCl is more stable than Cl2 as a sigma bond. So it makes it exothermic. And since we could also look at entropy, we've got 2 moles of reactants, 2 moles of products. So delta S should be pretty close to 0. There's similar quantities of entropy on both sides. So that's why the exothermic nature is what determines the sign for delta G. And when delta S is close to 0, this whole term gets close to 0. And so whatever the sign is for delta H, that determines the sign for delta G. And so if we have a decrease in potential energy because the products are more stable than the reactants, that's what drives the process forward thermodynamically. As with some of our other reactions, fluorine is not very practical because of its reaction so vigorously, so violently, produces a lot of energy, and it's not selective. It will start reacting at any position here, and that's not going to give us the product we want in a controlled way. And iodine is too stable. It's a larger atom, it's relatively stable, so it's not as reactive, and that means starting off at a lower energy, kinetically, it's too slow. It takes too much energy in its collisions to reach a transition state, so it doesn't really react very readily, which makes it hard to make much product in a given period of time. So we're focused mostly on chlorine and bromine here, which is fine, because those elements are involved in the other reactions for the most part that we've seen anyway. So this is the generic mechanism. Anything that's strong enough of an electrophile can attract these electrons out and form this resonance stabilized sigma complex with its resonance stabilized carbocation. Then any base around, even a very weak base, and what we saw in the last reaction was a Cl minus or a Br minus. We've been saying since last semester that these are such weak bases, we never see them even pick up a proton. But here's a situation where they could pick up a proton because re-aromatizing the ring is such a favored process to occur. So picking up the electrophile, resonance stabilization, re-aromatizing are the main key steps of any electrophilic aromatic substitution reaction. So let's look at a couple other variations. One occurs with fuming sulfuric acid. What fuming sulfuric acid basically means is that you've got sulfuric acid with SO3 gas. And so since this is a gas at room temperature, it's not easy to work with, but you can dissolve it into aqueous solution of sulfuric acid. And that gas will remain dissolved in there because of the intermolecular forces it can form with the sulfuric acid in the water. But the SO3 itself, even in solution, is quite electrophilic. Normally, if we look at this, we would say, well, this oxygen's more electronegative than sulfur, not by a ton, but by a fair amount. And so shifting those electrons away should create a large partial positive there. The partial positive here also exists because of resonance, and we can see the degree to which the center of that is blue and positive versus the negative on the outsides. So a nucleophile, like an aromatic ring, will be nicely attracted to the sulfur. What's also true about the sulfur here, though, is that in resonance, the major contributor is actually not going to have double bonds there. So we can draw it like this, because sulfur can have more than 8 valence electrons around it. And this is what would be needed to balance its formal charge. But we can also imagine through resonance each one of these pi electrons moving out to create a lone pair. And if that occurred, there'd be a negative on each oxygen and a 3+ on the sulfur. So that's a lot of formal charge. It's enough positive to attract these electrons in to some extent. But the stability of these pi bonds is significantly less than the stability of like a carbon-oxygen pi bond. Because carbon and oxygen, or carbon and carbon even, two elements in the same energy level have roughly the same size p orbitals. So when they overlap their p orbitals to make a pi bond, the overlap is pretty good. Anytime elements of the same energy overlap their p orbitals side by side, you usually get a pretty decent pi bond. Oh, excuse me. But the sulfur, this is a 3p, and the overlap between a 3p and a 2p is kind of mismatched. The meaty part of the 3p is up here, the meaty part of the 2p is down here. They're just not aligned very well. So we don't get very good overlap. And that means that these pi bonds are really very unstable. And so the major contributor is the one that has all this formal charge. And so in reality, the amount of charge on the sulfur is not just a significant partial positive due to electronegativity differences, it's a very large amount of positive there. So that makes this SO3 a really nice electrophile. The degree to which this sulfur has positive is much more than just a partial positive. And so it will very strongly attract in the pi electrons from an aromatic ring. It makes it a really nice electrophile there. So the aromatic ring will attack. It'll create this intermediate. The carbocation stabilize through resonance. And then this proton needs to be picked off just to draw the resonance contributors real quick. If this electron pair moved in, you'd have the positive charge here. If this electron pair shifts there, you'd have the positive charge here. And those three would all be in resonance with one another. So that helps to stabilize the carbocation. But it would be a lot more stable if we could re-aromatize the ring. So that's what happens next. Once the resonance stabilization occurs, in this case the best base around would be water, since that would be the solvent for the fuming sulfuric acid. So the water would pick up that proton, re-aromatize, and you'd form this product. And in this case, this would be an equilibrium because this proton is quite acidic, given that when it's released, the negative charge here would be stabilized through resonance on all three of these oxygens. So that could go back, and this oxygen could be negative, or it could pick the proton up and shift back and forth. The main thing here, though, is you've added a sulfonate group to the aromatic ring. So if you're trying to create a molecule that has a sulfonate group bonded to an aromatic ring, you can use this reaction to do that. You can also use similar conditions to shift the process back. And that's an equilibrium that we'll look at in more detail after spring break. So don't worry about the details for that right now, but you should be aware that it can shift forward or backwards, and you can control that equilibrium. Another reaction that you can do on an aromatic ring is with nitric acid and sulfuric acid. And these have to be concentrated, and that means they're pretty dangerous. The fuming sulfuric acid is also quite dangerous, given how unstable and reactive it is. And in this case, we need reagents that are pretty unstable because the aromatic ring is quite stable. And if we started with a stable aromatic ring and a stable reactants, then they'd be really low in energy, and it would take too much energy to get to the transition state. It wouldn't happen often enough. So kinetically, it wouldn't be practical. Even if the product were more stable, if the activation energy is too high, kinetically, we might not be able to reach a temperature in which the product can be produced in a significant period of time without causing other side reactions. So we need our other reactants to be pretty unstable. We need to create a really strong electrophile that will be unstable enough that the combined instability of the ring and the other reactants will be high enough so that even reasonable collisions will be able to get to that transition state. So this reaction works quite well most of the time. What happens here is first, the nitric acid and sulfuric acid react together. Nitric acid is a strong acid, sulfuric acid is even stronger. And it's so strong and it's so much more stable after it loses that proton, it will actually force the nitric acid to act as a base and pick up a proton. And once that does, it creates a great water leaving group. So this oxygen swinging in and pushing that out can create the nitronium ion. And this is the electrophile that the ring is going to attack. So the ring doesn't really react with either of these reactants directly. They react together in situ or in the reaction to produce this nitronium ion and a water molecule, which helps the process move forward because that is favored by entropy to produce an extra molecule, and water is relatively stable. But the nitronium ion is pretty unstable, and so that starts relatively high in energy, and even weak collisions with the ring can get over the transition state. And so what would be happening there is the ring would attack the nitronium ion, pushing electrons out to the oxygen. That gives me an NO2 group, just to point out what that NO2 group looks like. Oops, didn't mean to draw that. Let me try that again. Once that pair of electrons connects to the nitrogen, and the electrons swing out there, the nitrogen will still have an NO double bond and an NO single bond. And that will, then once I put in the formal charges, it will look like this. So this is a nitro group. NO2, usually you'll see it abbreviated this way, but sometimes you might see it drawn out structurally, and that's an NO2 group. So we need to re-aromatize the ring here. So what would happen to this next? Obviously it's resonance stabilized, so this would be the sigma complex. And if we wanted to draw the hybrid real quick, it would look the same as the other hybrid structure, where the resonance extends over these atoms but does not extend to the sp2 hybridized carbon. So it can't extend through the nitro group. And then there's a partial positive on 3 of the carbons of the ring instead of a full positive on any one of them. And that really helps to stabilize the carbocation. But as we said, it would still be much more stable if it were aromatic. So the best base around, which would be the solvent for the nitric and sulfuric acids, which is water, would come in there and re-aromatize the ring by picking off a proton from the same carbon that attacked the nitronium ion. Because that's the only way to re-aromatize and avoid a 5-bonded carbon here, and also complete the noble gas configuration for the carbocation. Questions about that? All right. Once you do that, the nitro group can be reduced to an amine. So all we need here is a metal that has electrons it's willing to donate, and iron and zinc are both good options, and an acid to donate a proton. So the mechanism here we're not going to go through, but I want to give you at least a general idea of what's involved in that mechanism. So if the nitrogen bonded to these oxygens, if the oxygens start picking up protons, eventually when the oxygen picks up enough protons, it'll become a water-leaving group. And then the iron or zinc will provide electrons to the nitrogen to push that oxygen out. And then those electrons will pick up more protons. So eventually the oxygens get protonated and act as water-leaving groups. The iron or zinc provides electrons around the nitrogen, because right now it doesn't have any, right? These oxygens are going to pull the electrons away since they're more electronegative than the nitrogen. So we need these electrons to surround the nitrogen, and then the nitrogen can use those electrons to pick up more protons and form an amine. And this reaction works relatively well, so it's just another tool in our toolbox to control the structures and functional groups present in molecules. So if you want to go from a benzene ring to aniline, you can do the nitration reaction first, which would convert the benzene ring into nitrobenzene, and then use the reduction conditions to convert the nitrobenzene into aniline. So it's a two-step process. So you want to think about that and work with it in some examples so your brain gets used to seeing that pattern where you can install an NH2 group on a benzene ring. All right, so another reaction that you can do is to connect a carbon group or an alkyl group. Right, an alkane, we all know, is just a hydrocarbon with no double bonds or triple bonds. So an alkyl group is just a substituent, like a methyl, ethyl, propyl. So if we want to install some carbon group as a substituent on an aromatic ring, we can try to utilize this electrophilic aromatic substitution reaction. We know that the ring can act as a nucleophile. We know that we can make an alkyl group an electrophile. If we have a leaving group, we could imagine the ring attacking that, pushing that out. If that worked, we would want to make sure we count the carbons so we don't make a mistake in the structure. That would potentially go through an EAS reaction. Maybe the Br minus or some other base could be used to rearomatize and produce a benzene ring with a carbon group attached to it. The problem with this as it's shown is that the reactants are too stable. Even though the product looks relatively stable, if the reactants are too stable, then getting to this transition state, well, this is intermediate, getting through the transition state to get to this intermediate would require too much energy and it would almost never happen. So we need something to facilitate this reaction. We need something to help the bromine leave and make a better leaving group if we want this to be effective. So at the moment, it looks like it could work, but from a kinetic perspective, the reactants are just too stable. We need something less stable to make a stronger electrophile, something that wouldn't be as stable so that it can get through that process without requiring such strong collisions, which would almost never happen. So we can go to our toolbox and pull out our Lewis acid catalyst. So we already saw how this positive charge on the aluminum can attract in a lone pair from a chlorine. So here what we would see is the same thing. This chlorine, we would help it to leave by making it an even better leaving group by using the Lewis acid and having the chlorine connect to it. So let's take a look at that. So what role does the Lewis acid play? It makes the alkyl group a better electrophile. And so what we're going to see here is how that works. So what would happen is, as we just showed, the chlorine would attract to the aluminum. And again, this aluminum looks neutral. It doesn't have a formal charge, but the electronegativity difference here is so big, and the aluminum really needs to be without those electrons to make its noble gas configuration. It's going to have almost a 3+ charge there. So that's going to attract the partial negative of the chlorine in there, at least temporarily. It could shift back. Right? The chlorine could pull back out and go back, or it can move forward. Excuse me. But if the chlorine then takes on a positive, it also makes it a much better leaving group from the carbon, because positively charged atoms are even more electronegative than neutral atoms, and it'll start pulling these electrons much more than normal. And as long as the carbon can stabilize the carbocation that forms through some degree of hyperconjugation and induction, the chlorine could act as a leaving group there. So basically, the Lewis acid facilitates the chloride leaving group, making a much stronger electrophilic structure in the form of a carbocation that's not stabilized by resonance. So we generated a carbocation that's not stabilized by resonance, and so this is really quite unstable. By forming this, you're basically forcing the ring to attack that carbocation. And I think we have space here to show the full mechanism. So when the ring attacks the carbocation, any one of these pi electrons can do that. I'm going to number these 1, 2, 3, 4. So it's carbon 3 that would be attacked. Obviously, that's the carbocation. I'll make sure I connect the structure with the right connectivity. So this pair of electrons right here would now be here. So there's no pi electrons around this carbon. It becomes a carbocation. Electrons can shift over here, so we have the resonance stabilization of the sigma complex. These electrons can shift here. So there's, again, 3 resonance contributors contributing to the stabilization of that carbocation. So if I'm starting with a carbocation that's only stabilized on a secondary carbon through a little bit of hyperconjugation and induction, it's stable enough to form. A primary carbocation wouldn't form, be too unstable. But we could form a secondary one. So once that forms, though, the ring will react with it pretty easily, because now it's better to have the carbocation stabilized through resonance. And then the last step would be very similar to what we saw before. Since this now has too much negative around it for the amount of positive there is, one of these 4 chlorines will break away and pull off a hydrogen from the same carbon that the electrophile got connected to, so that those electrons can swing in here and re-aromatize the ring to form a product that is now conveniently connected to a carbon group of our choice. So again, controlling the group of atoms that's connected to the aromatic ring. So we just took a look at what would happen if our leaving group were on a secondary carbon. It should do a decent job. The yield's not great, but it should do a decent reaction here where we get the ring to connect to that secondary carbon. So we want to compare that process and the outcome we get with a slightly different situation where if the leaving group is connected to a primary carbon. And in this process, if we do this reaction experimentally, what we'll see is a mixture of products where typically the primary carbon connecting directly to the ring is a minor product versus this rearrangement product. And so we want to try to understand how this forms. So what would happen in the mechanism would be this very similar to what we saw in the last mechanism, especially in regards to the first step. What we saw before was the chloride leaving group would attract to the positive charge of the aluminum, and this might be even more of a dipole ion type attraction because the aluminum has so much charge it would at least attract through a charge attraction the partial negative of the chlorine in there, and that would start sharing electrons with the aluminum a little bit. And that creates a large positive on the chlorine there, which is what we're showing here. So now there are two things that can happen at this point. What you should not do is to show the chlorine leaving to produce a primary carbocation. Primary carbocation is too unstable. So don't do that in your mechanism. If you have the leaving group on a primary carbon, it really can't just leave because the transition state and intermediate that result from that are too high in energy. So that's one option you could imagine, but you should exclude from the reasonable mechanisms that you would consider for that reaction. So the other two options, which are responsible for the production of these two different products, look like this. So one, there could be a hydride shift that occurs as the leaving group is leaving. Right? So we don't want to produce the primary carbocation and then try to do a hydride shift because it would never get this far. The primary carbocation is too unstable. I keep using that space to draw, but I need it to draw something else. So instead of the leaving group leaving behind a primary carbocation, the hydride can shift over and as the leaving group's leaving and form a secondary carbocation, which is at least stabilized with more hyperconjugation and induction, and so that should be able to form. Excuse me. Once that forms, then the aromatic ring can attack it just like we saw in the last example. So electrons will be pulled away, producing a carbocation that's stabilized, and then the chloride would come over here, pick off this proton, and re-aromatize the ring. And that produces the major product. So the major product is the one that involves a secondary carbon bonded to the ring, even though we had the leaving group on the primary carbon. And so the reason that works is because the hydride shift avoids the unstable primary carbocation and produces a secondary one instead. So what if you want to make this product? There's an alternative way to make this in a higher yield than this percentage. But you could do this reaction and then try to separate out the major product and just collect the minor product. So the disadvantage there is you wouldn't get much. The yield would be quite low, so it's not the optimal way of forming this. But we do at least want to understand how it forms. So alternatively, instead of the hydride shifting, what could happen here is once this forms, instead of the hydride shifting over, is maybe the aromatic ring just attacks it in an SN2, right? This is a primary carbon here. It's not too crowded. The ring isn't supermassive. And so it can come in here directly and push the leaving group out. So without doing the intramolecular hydride shift, just have the benzene ring attack. But you should know that that's a minor product because that doesn't happen as often as the hydride shift. Why does the hydride shift occur more often than the benzene ring attacking? Well, it's because it's intramolecular. The hydride is already right there. All it has to do is align the sigma bond with the sigma bond here, and then when this one leaves, it just simply jumps over. It doesn't require this structure to collide with anything else specific. It just requires the structure to collide some way, somehow, with enough energy to shift that hydrogen over as that happens. So that's going to happen more often than the benzene ring coming in and specifically attacking there. And so that's why the major product occurs through the intramolecular hydride shift versus the intermolecular attack of the benzene ring on the primary carbon. But that can happen. So if that attacks, I would then have this 4-carbon chain connected starting from this because it would be attacking the primary carbon there. And that would produce the carbocation. It'd be stabilized by resonance. And then the chloride, similar to the other mechanisms for the same reaction, would pick up that proton and rearomatize. So that is how I would get the substitution where I'm adding a butyl group rather than a sec butyl group. So, as we were saying, if I want to make this product, this is not the way to do it because I only get a 65% yield. Right? If I want to make that, well, I didn't get a much better yield here anyway. So maybe that is fine, but in this reaction, I generally don't want to do a reaction where I'm forming two products, significant amounts of two different products, because then, especially if they have similar properties, it's not easy to separate them. Maybe one has a lower boiling point than the other, maybe one is passing through silica a little faster than the other, so I could separate them through chromatography, but they look really similar. It's going to be hard to utilize, to take advantage of their different properties and separate them from one another. So the Friedel-Crafts alkylation has some limitations that we're seeing. Just to answer these questions, we said, why would the hydride shift occur more readily than direct attack? And that's because it's intramolecular, which we just described. And why are reactions that give mixtures of products impractical? Because it's hard to separate. We just talked about that. It's hard to separate the components of a mixture when they have similar properties cleanly. So we were just saying, the Friedel-Crafts alkylation has some limitations, which we've already seen some. So one limitation, oh, well, there are 3 additional limitations. One limitation is it won't work well when my leaving group's on a primary carbon. And as we just said, when my leaving group's on a primary carbon, I get a mixture of products, and that's a mess. I have to try to clean that up and isolate the one I'm interested in. And either one I don't get a very good yield of because they're both not very high yields. So that's one limitation. Another limitation, I can't connect groups to the ring that are sp2. So obviously, we've talked about this, you can't get the leaving group to leave from an sp2 hybridized carbon because the resulting carbocation would be too unstable. It would be an empty sp2 orbital, which is relatively compact, and it's really difficult to pull electrons out of that spot. So this would require an even stronger activation energy. Even with the catalyst, it's not going to pull off that leaving group and create a really unstable carbocation. So that's another limitation synthetically on what I can do with this reaction. I can't use an alkene or an aryl group as my electrophilic group with the chloride or bromide leaving group and then have the ring attack it. Another limitation, and this may be a limitation, it may not be depending on the product you want to make. So let's take a look at this one. What would happen here? The aluminum would attract in this chloride. The chloride would become positive. It would pull electrons away from the carbon. So that would produce aluminum with 4 chlorides. And the carbon then would be without that, so it would be a carbocation. And this would be tertiary, so it would form pretty readily. And then the ring would attack it. It would end up connected to the ring. Once that occurs, there's nothing to prevent the same structure now from attacking a second tertiary carbocation. So this is what the quiz question for today was about. So let's talk about that and do the mechanism for this. So we showed part of that mechanism already. We showed how to get the carbocation to form. So the ring would attack that. Oops. Go back. Made a mistake there. The ring would attack the carbocation. It wouldn't be aromatic anymore. The resonance would stabilize the carbocation there. And then this chlorine would kick off this proton to rearomatize the ring. So once that occurs, this group actually makes the ring more reactive than it was initially, a little bit. So this is a concept we're going to talk more about after spring break, but I wanted to give you a little preview here of what you're going to see and why that is. So you might think, well, it's a pretty sterically hindering group. It's going to block things from colliding. It should slow down the next step. It shouldn't allow this ring to be as reactive as the other one. And that's a reasonable hypothesis, but this torpedo group is only really creating sterics in the area roughly around it. So I can use sterics to explain why I would not see a reaction at this carbon or this carbon because the collisions there would be blocked by this torpedo group. But the site on the opposite side of the ring is pretty open. So if another tertiary carbocation forms, it can react I've already got one terbutyl group connected there. And now the other one ends up being connected. And that produces a carbocation. All right, so let's look at this carbocation versus this one. In this carbocation, there are 3 resonance contributors. One, two, and if these electrons swing in there, I get the 3rd one. For this structure, there are also 3 resonance contributors. So I got a hydrogen here, just like I had a hydrogen here. So the resonance would not extend onto the sp3 hybridized carbon, obviously. So this pair could shift here. That'll give me a carbocation here. 1, 2. And this pair could shift over. Which would give me the 3rd resonance contributor. So what am I noticing here? Well, the first step requires this ring to attack this tertiary carbocation and form this intermediate. Right? When resonance occurs, none of these structures exist. What exists is the average or hybrid. So let's take a look at that hybrid. The hybrid would have resonance over 5 out of 6 of the carbons of the ring, a partial positive here, here, and here. So that partial positive is spread out over 3 secondary carbons. Over here, again, we're forming resonance. So none of these individual structures exist. What would exist would be the average or hybrid. If we draw the hybrid for that, we've got resonance extending around here in the same way we did over here. But now there's already an alkyl group on here. And when I look at where the partial positive is shared, one of those carbons that shares the partial positive is tertiary. So the collision in the first alkylation of the ring produces an intermediate that's pretty well stabilized through resonance, but all the partial positives are on secondary carbons, which is not quite as stable as the tertiary carbon stabilizing that positive because of the extra induction and hyperconjugation that allows electrons to shift in. So because this terbutyl group is an electron donating group through induction and hyperconjugation, shifting electrons in to stabilize this positive, once that group's installed on the ring, it's easier. It doesn't require as high of an activation energy or transition state, and the intermediate's also more stable when the collision occurs here because the resulting carbocation is stabilized better when the positive is spread out over carbons that are tertiary rather than all 3 of the sites being secondary. So in this reaction, it's very difficult to avoid that occurring. So just to finish the question here, what would happen next would be the chloride from an AlCl4 would come in and pick up a proton to re-aromatize the ring. And so you would get a structure that has those 2 terbutyl groups on opposite sides of the ring. Now, for the quiz question, I wouldn't necessarily expect you to go there unless I wrote excess. Excess would imply that you've got more than enough moles of this to do substitutions at both sites on either side of the ring. But you should know moving forward that with this reaction, an alkyl halide, especially a tertiary one, with the aluminum chloride catalyst on an aromatic ring, it's very difficult to prevent substitution occurring at more than one site, even with the sterics, specifically because once one terp-butyl group is installed, it facilitates the installation of the next one due to stabilizing the carbocation intermediate through hyperconjugation and induction more effectively. So that's a second limitation. If I only want to install one group, this is not the best way to do that because it's difficult to prevent multiple groups from attaching to the ring. And the third limitation is if the ring already has a group attached that is a highly electronegative group or attracts electrons from the ring out through induction or through resonance, then this reaction doesn't work. Right? What we need to happen here is to form a carbocation, and we need the ring to attack the carbocation. That means the more electron rich the ring is, the more partial negative or negatively charged electrons there are in the ring, the more they'll be able to connect to the positive of the carbocation. So if I have a group here like a nitrogen or oxygen or fluorine, something with a positive charge, and when that nitro group is there, it actually looks like this. So there is a positive charge on that nitrogen. Through induction, it's pulling electrons away. That creates a lot of partial positive right there. Through resonance, these electrons can swing out here, which can pull electrons out of the ring. So that creates a positive here, and then those can swing around, which creates a positive here. Those can swing in, creates a positive there. So there's a lot of positive on this ring. A ring that has a lot of partial positive is not going to attract to a partially positive carbon, because obviously like charges repel. So that's why this reaction is not going to work. I can't get this ring, if it's got areas of partial positive on it, to readily connect to this carbon. If I increase the temperature enough and facilitate collisions enough, I might be able to get to connect here or here, since these two carbons don't have partial positives, or very much at least. But it makes this reaction very difficult, and it doesn't give very good yields. So we're going to discuss that concept more later in the semester, but we wanted to point that out. So I might ask you a question on the exam after spring break. It might say something like, describe the limitations of the Friedel-Crafts alkylation reaction. And so there are 4 of them that we discussed, just to review those again. The first one was, if you have your leaving group on a primary carbon, you get a mixture of products. It's a major limitation. It's very difficult to use the Friedel-Crafts alkylation to make a primary carbon group connect to the ring. The second limitation we said was we can't use vinyl or aerial electrophiles and get the ring to attack them because we can't get those leaving groups to leave behind a carbocation on an sp2 hybridized carbon. The third was it's hard to avoid multiple R groups substituting on the ring. So if we want multiple R groups, then that's a great option. It's a great reaction to do that. But if we only want to install one, it's difficult to do that without getting the other one connected as well. And then lastly, if there's already an electron withdrawing group, a group that attracts electrons out of the ring, it makes this reaction much slower and impractical as a result. So, an alternative to alkylation is called acylation. So here, instead of installing an alkyl group or an alkane substituent, we're going to install an acyl group, which has a CO double bond. And so the way this reaction works is pretty similar, actually. The difference is not in the first step, because in the first step the chloride would still attract to the catalyst, and then after that it would still leave. So that's what we're going to see happening here. It's going to attract to the catalyst, it's going to leave, and when it leaves here from this carbon to create a carbocation, that is stabilized through resonance. And so the carbocations we saw for the alkylation we're only stabilized through hyperconjugation and induction, and resonance is more stabilizing. So this is called the Acelium Ion. The Acelium Ion has a carbocation on a carbon that's doubly bonded to an oxygen, and there's resonance there, which you can see right here. So the positive isn't really only on the carbon, it's actually also on the oxygen, shared between both at the same time. And sharing the positive over both of those atoms really helps to stabilize it. So that means now that can happen at the end of a chain on a primary carbon. We can make a primary carbon. It's basically a primary carbocation, but stabilized through resonance with the oxygen. And so that prevents the possibility of rearrangement. So we don't see the rearrangement. Once this carbocation forms, it's stabilized by resonance, so it won't rearrange. And then once it forms, the rest of the reaction is basically the same. The aromatic ring that we would have would attack that. And now that one of these two carbons that this pi bond was shared between would be connected then to this carbon, which would still have the double bond to the oxygen and the other R group attached. The other carbon of that pi bond would be a carbocation, and the other two pi bonds would still be there. That would be stabilized by resonance. And then just like always in these reactions, whatever the best base is that's around, it could be a chloride from the aluminum chloride to regenerate the AlCl3 catalyst, would re-aromatize the ring. And now we've got this ketone group or acyl group substituted onto the ring, and we regenerate the AlCl3 Lewis acid catalyst. So that's a nice option. Maybe we want to make a molecule with the CO double bond connected to the ring. This is a great way to do it. Alternatively, if we really wanted to make this structure, that was our goal a while back, right? Remember we were talking about this structure back here. We said if we want to make this, this is not a good route because it's a minor product. We have to remove the side product. We won't get much of it. But if you want to put a primary group on a benzene ring, there is an alternative, and that is to start with the acylation, which is the reaction we just saw, and then reduce the CO double bond to a CH2. And there's a few different ways to do that. One is called the Clemmensen reduction. So I do a Friedel-Crafts acylation rather than an alkylation to avoid the side product and the rearrangement product. And then I use similar situation to do a reduction. So I have a metal that provides electrons and an acid that provides protons. So the protons bond to the oxygen, making it a good leaving group. The electrons come in, connect to the carbon to push that out, and then those electrons pick up another proton to make new CH bonds. So this would be a preferred route. You get a higher yield, you don't have the side products to deal with, and that's what you would want to set up if you're trying to connect the primary alkyl group to a benzene ring. We were saying a minute ago how it's difficult to avoid polyalkylation. And we were saying the reason for that over here is because once one group is installed, that group facilitates the installation of the second group because that group donates electrons to stabilize the resulting intermediate through hyperconjugation and induction. Well, we don't see the same thing with an acyl group. So I don't have to worry about the polyacylation like I was seeing polyalkylation. Right? So the reason for that is once this is installed, this group is an electron withdrawing group. Imagine what would happen if this occurred again to produce another Acelium ion. pi bond comes out here to connect to it. Maybe it would connect here to that carbon. These other two pi bonds would still be there. There'd be a carbocation here. So that's not a problem because the resonance can stabilize the carbocation. But having this group already on here, what effect does that have? Well, the oxygen is pulling electrons away through induction, which is putting a big partial positive on this carbon. And so when these electrons shift through resonance, as we're analyzing all the carbons of the ring that help to stabilize that positive, we would see there we get a positive there. And putting that right next to this positive is going to make it pretty unstable. So once the first group is installed, colliding with the second group to do poly substitution would not be as likely, because if it did occur, the carbocation that would be produced would be shared over a carbon that's right next to another positive. And those two positives next to one another will cause a lot of repulsion and make it pretty unstable. So if this is an R group, it facilitates a second substitution. If it's a CO double bond R group, it deactivates or inhibits, is a better word, the installation of a second acyl group on the ring. And so if you want to install two acyl groups, that's a disadvantage. But if you only want to install one and then do some other reactions to that and not have a second one connect, then this is a better option. So we get the polyalkylation, but we don't see polyacylation. And we're gonna discuss that again after spring break, but I just wanted to explain how the electron withdrawing nature of this oxygen creates a positive that would destabilize this if it were to try to react a second acyl group onto the ring. So that's not likely to occur. And so that's the basics of the electrophilic aromatic substitution reaction. After spring break, we're going to see a lot more electrophilic aromatic substitution reactions with a lot more examples. We're going to see examples where you already have a ring that maybe has some group already substituted on it. How does that affect where the next electrophile might connect? So we're going to see issues where there are regiochemical considerations to make, where that electrophile might add to some of these sites but not others. And there are also kinetic issues, depending on whether this group that's already attached attracts electrons or donates electrons. That will have an impact on the regiochemical and kinetic aspects of that reaction. So that's what we're going to talk about next time. So there's not many bullet points here, but you can see that we talked about a number of different EAS reactions, and you've got to know some details for each one. So even though there's only a couple of bullet points, there's a fair amount of detail there. So you should definitely practice those concepts with these examples in the textbook. And then next Monday, not this coming Monday, that's obviously spring break, the following Monday, we're going to continue with chapter 19 and look at some more EAS reactions. So those videos should also be helpful to you as well. So I hope everyone has a fantastic spring break, and y'all get a chance to catch up on some work maybe, but also have some time to relax. And that's all I have for you today, so feel free to reach out with some questions now or anytime.